We discuss various type of AC circuits, which means I can connect maybe a resistor and a capacitor together. Just one resistor, one capacitor together, and then put a AC voltage supply into this. If I do that, then you know this capacitor will create some sort of reactance effect, right? So that we discuss very in detail, X of C, which is 1 over 2 pi F times C. So this effect clearly showing that even if I keep the voltage apply right here fixed, but if I start change the frequency of the AC voltage, as a result of that, Xc should be a function of frequency. In this case, it is inversely proportional to the frequency, right? So if I can measure this Xc by using multimeter through the capacitor, which means by measuring the voltage across capacitor and the current passing through the circuit, the X of C I should be able to measure. If I do that, then I should be able to observe this behavior, right? So that's a very simple experiment. So that's our idea for today's experiment. We want to really see if the chapter number 15 concept which we built are true. Chapter 15, we discuss various things with the AC voltage supply. If all of those concepts are true, then I should be able to observe X of C is actually a function of frequency when I keep the voltage constant. And X of L should be a function of frequency, 2 pi F of L. And if I combine this, for example, if I combine this, all of these into a RLC series circuit, then we got an answer look like R square plus XL minus XC to the power 2 square root of that. So all of these again, this also a function of frequency. So all of these theorems or basic ideas we develop on chapter 15 should be true if I have AC frequency, if I keep the voltage constant without changing that magnitude, but I can change the frequency only on the AC voltage. If I do that, then all of these things should be able to observe. So that's the simple plan. Today's experiment is nothing much to do. We just want to really see whether the basic ideas, the basic physical concept we discussed on chapter 15, whether those are true or not. That's the idea. So to do that, we need the setup. So our setup is very simple. So I can have either RC circuit, RL circuit, or RLC circuit, right? If I have this circuit, I can measure voltage across capacitor and the current passing through the circuit. If I apply the Ohm's law to the capacitor, then we know capacitor voltage should be equal X of C times the I. So from that, I can actually calculate the X of C with the measured voltage and current. So this going to be now measured value of reactance of the capacitor. Now on the other hand, I can actually calculate that X of C, which is equal to 2 pi times the F of C, by simply knowing the frequency of the applied voltage and the capacitance. I can actually calculate that. That's our theory part, right? So that's our physical principle we discussed on last chapter. Now, if these two are matching each other, then I can compare X of C measured value versus X of C calculated value. So if I get in the same numbers for these two, for example, the percentage error we can measure. If that is very small, then we can confirm that all of these theories we discussed on chapter 15 is true. So it's a very simple idea. And we can do a little bit more than that, because for capacitor X of C, which is a function of 1 over 2 pi C times 1 over F. So I can maybe look at that in terms of graphical picture. By using the graph, we can maybe make two graphs. I can make a graph frequency versus x of c, and O, I can make a graph 1 over frequency versus x of c. If I do a graph frequency versus f of c, this should be inversely proportional, so it should be decreasing. But if I do the x-axis as a function of 1 over f, then this should be linear. If I take the slope of this graph, so now this is the graph we are making, so the slope should be equal to 1 over 2 pi c. From there, actually, we can calculate the capacitance, which is simply equal to 2 pi times the slope of the graph. So this capacitance we know, then we can compare this calculated capacitor with the known value. So if I compare them and then percentage error again very small, then that also confirms all the concept and theories we build on chapter 15 for this particular scenarios by using the AC voltage. So that's the idea. So the measurements I need, we can do actually even without oscilloscope this experiment. We don't really need the oscilloscope because I just need to measure the voltage here, and by using the either voltmeter or the oscilloscope probe, or I need to measure the current passing through the circuit here. So those actually can be measured by without the oscilloscope, but we'll use the oscilloscope then because in the last part of the experiment, that also can be done without oscilloscope, but if we have oscilloscope, we can actually see the whole wave function. So that gives us a really good idea about what's really going on in this kind of a circuit, okay? That's our plan, which means we can investigate the same for RL circuit. So in that case, we need the resistor, and then we need the inductor, and then we need the AC voltage supply. Then we do the same thing again. We'll measure the voltage here for the inductor, that will be VL, and then we'll measure the current here. And then we know X of L is 2 pi F times the L. Then we know, of course, this is directly proportional to each other. So we can do the same thing again. We can make a graph X of L versus the frequency, then that should be very linear. If I take the slope of the graph, that should be equal to just simply 2 pi times the L. So from there, we can calculate the L, that should be slope over the 2 pi. Then we can compare that with the known value. And again, we can do the X of L by measuring the voltage across L divided by the current. Then these two, we can actually compare again, these two values, because those two values should be exactly the same. If I getting the percentage error low, that means our concept and theories we built earlier chapter is actually correct. So that's our plan. Any question? Okay, then we'll finally we'll do the RLC circuit, only serial one we're going to do, but you can investigate any other circuit because you know the simulator, how to use it. So we'll do RLC series circuit because that series circuit has a specific property. So I have a resistor, inductor, and the capacitor. It doesn't matter actually how these are connected. It no need to be necessarily RL and C. You can put RC and L or resistor in the middle, doesn't matter. Only thing what is needed is actually all three should be parallel, serial to each other, okay? And then we'll put the AC voltage supply. Then in this case, we would like to measure the voltage total, actually, how it going on from voltage here and the current total from here. Then we know X of RLC. In this case, we generally call the impedance. If I consider all three of them together, right? Z of RLC, which is equal R square plus X of L minus X of C square root of that. Then if I measure voltage and current, then we can calculate the C, that's going to be total voltage over total current. Then we can compare these two. If same, then our theory is correct. Now, on the other hand, we know if I change the frequency by keeping the voltage applied constant, but if we change the frequency, then we know this circuit behave very differently than any other circuit, because we know the power can maximize at one certain point. Power is simply, in this case, P equal V0 I0 cosine phi divided by the 2, right? Because of V0 we keeping constant without any change, then we know power can be maximized only when I0 actually maximizes, which means this circuit will give us a very different observation than the previous. If I try to detect the current as a function of frequency, then we will see current is actually slowly maximize and then disappear again as the frequency goes to the higher range. So that is actually what we call the resonance point, right? Which means when the maximum current is happening, the power becomes maximum. That called the resonance point. We can actually measure these values directly. What is the current max? And then accordingly, what is the resonance frequency measured? Then we know resonance frequency can be calculated 1 divided by 2 pi LC square root of that. So then we can compare these two values, the value observed from the graph to the value calculated. If those are closely matching up, then that reconfirm again the every single physical principle we build on chapter 15 is actually true. Okay. So that this extremely important experiment in a way, because otherwise chapter 15 look like very abstract concept and theory we build there. But by doing this experiment, you can really get an idea that those are not just abstract. Those are the really what happening if I have AC voltage in a circuit. Okay, that's the overall plan. Any question? It's fairly very easy experiment since we used earlier the simulator. I think the use of simulator should not be a problem at all. Then we'll continue into the simulator part. So that same multisim simulator, you have to log in. If you remember the last login detail, just use the same. And then we just need to do the setup first, our circuit, right? So the first we'll do the inductor circuit. So we could do actually many things than just understanding the inductance behavior. We could do actually inductor and resistor together too, RL complete circuit too, if we wanted to. Okay, but the first two, inductor and capacitor, I would like to see how itself inductor and capacitor behave in terms of AC voltage, whether it's the reactances are really the function of frequency or not. Then we can go on and then connect them together and then see how it is affected with the AC voltage. Okay. So we need the resistor and we need the inductor. Just keep the space between them to put the voltage sensor on. And then we need the AC voltage supply in this case. Usually I rotate the AC voltage supply negative to the right side because negative side should be grounded. Otherwise we have to do a couple of other things to do that. The grounding externally is actually the AC one. Then that's it. Then I need the switch. Then we can put the grounding somewhere here. Okay, then we'll connect all of these. All right, that's our simple circuit. And in terms of values we're picking up, we have to be careful, okay, because depending on this combination of these values, you can put any numbers as you wish, doesn't matter, but then you have to do trial and error, especially for last part of the experiment, then you have to do a trial and error to figure out where's the frequency range that maximum point is happening. That's so important, okay? Because if you look at that graph, the graph look like some sort of function has a maximum. So your frequency range, if I want to properly investigate this behavior, I should be on the range of frequency between here to here. Then only I can observe this maximum point, right? So that's very important. So if I investigating in terms of frequency wise this part only, then I will not see the maximum. This side only, I will not see the maximum. Frequency can go from 0 to any higher number, okay, hundreds of thousands or millions of values. So which means I should know before I start the experiment which range I would like to investigate in terms of frequency. Otherwise, there's there's no meaning doing this experiment, because if I don't know or have no idea about the resonance frequency, right? So the best way is to do that. The trick is actually we can calculate by knowing values here, and then we know the range we investigating. Then we can go back and select the range of frequency from F1 to F2. Then we know exactly that range maximum is there. Then I can slowly change the frequency to figure out exact maximum point, okay? So which means that initial condition, now the initial values of inductor and capacitor plays a major role. So we can pick any values, but we'll use the values given in the lab manual, then it's much easier because those values are already tested, okay? All right, so which means the resistor, you can put like maybe 45 ohms and the capacitor about 0.1 micro. This one will change into 45. This one will change into 0.1 micro. Inductor actually we are working on now, right? Inductor will use 15 milli. Let me take a look. Since the first table says the RC we'll do RC circuit first, I think. Get rid of this guy, we'll put the capacitor and then we'll do RC circuit first. It's not big deal. Okay, then the capacitor value will do 0.1 microfarad, okay. All right, so then we'll connect these two again. Doesn't matter actually which circuit you do first, okay, but since the first table says RC, I'm gonna start again from there. But if you want to do the RL, then I have to go with the table number 2 first, okay, nothing wrong, doesn't matter. Then the voltage doesn't matter, we can keep 1 volt, that not really a big problem at all. The frequencies actually matters, okay, so we'll start something like a smaller value and then we'll slowly increase to some higher value to see what will happen, okay. We can go like 1000 to maybe 10,000 range, doesn't matter technically. We'll do like maybe 500 and then we'll slowly increase from there. And we'll close the circuit and then simulate and then we'll look at the graph. So we need the sensors, voltage and the current, two of them, voltage sensor just before the capacitor and the current sensor somewhere in the circuit where you should be able to measure the total current passing through the whole circuit, okay? Doesn't matter which side you put that. That's all. Then in the graph, you will see the two lines as usual. Make sure the trigger into the auto. And now the green one should be our voltage sensor, the blue dot should be the current sensor. So I can measure the values from here very easily. You can make maybe this little bit is larger, then it's easy to observe. Okay. So only thing now I have to do is that take a look what will happen if I change the frequency. Okay, first we'll do that actually. So we'll change this number slowly. So if I change this frequency, you can see even from like 100 or 100 to maybe like 1000 range, if you look at it carefully, so the voltage maximum doesn't change much, okay? However, if you look carefully, the current wave actually changing a lot, okay? See that? So which means clearly either one is changing, that's good enough, okay? Because we know the reactance is actually function of frequency. Reactance, on the other hand, across the capacitor is actually the voltage divided by the current. So if you carefully take a look what happening to the current changing much as a function of frequency change, which means reactance will actually change. That's the idea. Okay, both voltage and current no need to be changes. Either at least one changing, which means the reactance is actually function of the frequency. That's what we're going to take a look. Okay. So we can start maybe like low frequency value, even like 100, I think. Doesn't matter the number exactly. So we'll start at about 100 and then we can increase slowly. Any question? Okay, if you click on the voltage and current, usually those becomes auto set the scales. And if you want to see at least one complete wave, you can use the time per division right now. I think everybody should be much familiar with those things. And then we need the cursors. We can use the track. Or you can use the either current value or the voltage value, because we don't need to really track because we are not interested in the x-axis numbers at all today. What we interested is y-axis values, okay? Left-hand side y is voltage, right-hand side y-axis is the current. I can put one into the voltage, other sensor into the current, then we can actually measure the both, okay? Y-axis, and we are interested voltage and current on both, okay? If I put the green into here, we know that should be about 1 volt. And if I want to put the current into here, maximum of this point, that should be about like 62.8 microamps. By knowing those two, I should be able to get the reactance. That number should be exactly the number we're calculating from the 1 over 2 pi fc, okay? That's what we're actually checking. Okay, so as usual, we'll collect a screenshot of this one. Insert illustration screenshot. So it's better to have a screenshot of all of these. Okay, then you can name this as usual. This is going to be figure 1. We can say this is RC circuit simulator with AC voltage. Okay. And then we'll go on to the table number 1. Frequency usually measured in hertz, that is 1 over second. The current is on amps, SI units, and voltage in volts. 1 over frequency we need because we would like to see that graphical behavior, okay? That's why that's going to be then 1 divided by the hertz. Reactance, measured in unit ohm. You can insert that symbol inside the symbols. You should be able to find that. And that's the same unit for the reactance, doesn't matter, measured values or calculated values, it's the same unit. And then we'll compare those two at the end, okay? Because we're expecting those to be exactly the same, we'll do the percentage difference. We will see a little bit of differences, maybe because of the rounding error, things like that. But otherwise, we should get very low percentage difference in this case, okay? Any question? All right, we'll start from like 100. Maybe we can add one decimal place purposely into here. Otherwise, it look like one significant figure. So we'll add one decimal place for the frequency. Okay, the current I'm measuring, doesn't matter, I measure negative side, but we interested in the magnitude. Okay, 62.868 equals 62.868 times 10 to the power minus 6. It is micro. And then it will auto adjust to the scientific notation. If not, make sure you put this into scientific notation. Okay. And that should show all the measurable decimals. In this case, we are measuring 5 significant figures. So I should be readjust this to show all the significant figures. Okay. Voltage is 1. It's since I'm measuring it, I'm gonna record the measured value 1.0062. That is a measurable error which happening because of where I can put this cursor is. Okay. 1 frequency you can calculate in a bit, but we'll take a look at the reactance. Okay, reactance we can calculate by knowing the equation that's going to be equal 1 divided by parentheses 2 times pi times frequency value times the capacitance, which is 0.1 microfarad, 0.1 times 10 to the power minus 6. And parentheses out, close parentheses, hit enter. Let me see this. Change this into maybe scientific. Oh, I know, because pi command should be pi open and close brackets. Okay, so that's the reactance value for the low frequency level. Okay, so that's fairly large number. We can keep like 1 or 2 decimal places. If it is really large number, maybe we should write it down that in scientific notation. That maybe looks better. So we can do in scientific notation with maybe I can have frequency around like 3, 4 significant figures. Because of that, we will keep at least 5 significant figures. We don't need to keep too many, okay? Not much meaningful. Let's check this with the measured value. Measured value means the voltage across the capacitor divided by the current passing through the capacitor, right? That just simply using the Ohm's law, okay? So if you look at it, those two numbers, 1.59 10 to the 4, 1.60 10 to the 4, it very, very close by, okay? That's the idea. So that confirming not just the ideas we develop on chapter 15, actually these are reconfirming everything we discussed very before that. For example, the idea of the Ohm's law again reconfirming. Ohm's law can be applied without any problem per every single item in any circuit. Doesn't matter what's the voltage we applied on, okay? It's going to be XC calculated by using the equation, and it's going to be XC measured by using the Ohm's law. X of C measured by using Ohm's law, then we'll compare these two equal ABS. Since we're doing the PD, doesn't matter which comes first. Difference between the two items divide by the average between the two items, right? F8 plus G8 divided by 2 multiplied by 100. And percentage errors never used the scientific. It should be number format and then at least 2 decimal places, 2 significant figures visible. Okay. So that's a very small, less than 1% error. So that's confirm everything we would like to investigate in this setup. Okay, guys, any question? Okay, let's do one more frequency also because we need that for the graph. I'm gonna use maybe scientific notation for that. That's going to be a smaller number with 4 significant figures visible. Okay. And we'll put that function also into here. That's going to be just simply 1 over the frequency. All right, then we'll take a look how this capacitor circuit behave as a function of increasing frequency. Okay, that's the plan. So we know the reactance must be a function of the frequency. So which means if I increase in the frequency, I should see that effect on these reactance values. Okay, so that's the idea. All right. We can maybe increase the frequency like 500 at a time. That's okay, I guess. We can go into maybe 500 next. And the graph is actually getting much squeezed with the higher frequency, then you know what to do with that, right? You have to change the time per division into a smaller values, smaller values, then you can see it clearly. Now you can see the current is actually goes away from the visible range. You can bring it back by clicking this, okay? Then it will auto adjust. Voltage doesn't change at all, right? It remains in the same point, the maximum, but the current value, it will auto adjust actually into the cursor. But its number is actually changes. The current now becomes 314 microns. So that increases by large amount relative to the previous value. Okay. So then you record everything. Now I'm on 500 hertz. The current is about 314.34 micro. 314.34 times 10 to the power minus 6. And the voltage remaining the same. Doesn't affect at all. And the 1 frequency you can easily do. All of these also I can easily calculate. And then pay attention to these two numbers. Okay, that's what really interesting. You can see it's the same number, which means reactance is changing, but our theory is actually very correct. Okay, these are directly what we are observing. So the theory is the one we calculated, the number, the equation we built on last chapter. Okay, by using the phasor diagram concept. Okay, any question? All right, then you can continue. You can increase the frequency. I would suggest we'll go maybe each 500 at a time. Then I can go 1500, 2000, 2500, 3000, 3500, and then 4000, and then 4500. So all you have to do is measure the current carefully. Now you know even voltage does not change at all, right? Because if you remember the capacitor RC charging discharging circuit, which we done earlier with the experiment number 9. So the capacitor discharging circuit, the charging discharging depending on the amount of voltage you apply. So the capacitor always going to charge into the maximum voltage you applied into the circuit. So that number doesn't change, right? If charging discharging process happening continuously with the rate of this frequency, which means the capacitor voltage going to remain in fixed, because that's what we actually observing. When it reaching this maximum point right here, it actually fully charged. Then it discharge and then charge again. That process going to continue. Okay. That's why the voltage value doesn't change, because that always going to charge into the same point. But the frequency is actually changing something in the capacitor. That's the current passing through. Okay. So that's the idea. Higher the frequency, it allows to pass through more and more current. Higher the current, higher current. Okay. And if you bring the frequency all the way back to the zero, then you can understand the DC circuit, because the DC, if you apply the DC power source into the RC circuit, the capacitor for the DC voltage acting like a switch, which means when the capacitor is fully charged for the DC voltage, capacitor completely block the current. So that's the idea. If you bring the frequency all the way to the zero frequency means technically it looked like the DC voltage. So the capacitor have a voltage, but the voltage does not change its polarity. So it like the DC voltage. If you have a DC voltage, capacitor will charge and then the current will fully block. So the current should become zero in that case. Okay, that's the idea. All the concept which we building has to match. Okay, you can't really build one concept for one thing and then the when you're moving into the next, then if there's no connection between those concept we're building, then that does not make any sense physically. Okay, the physically there is a connection, all of those ideas. Okay, so then we'll continue measurements. I think you can do on your side without any help. All you have to check carefully the current value now, okay? But look at the voltage too always. If voltage is changing slightly, we may have to record that, otherwise it will affect the error. But check it carefully, okay? All right, then we'll continue this into 1000 hertz. Voltage remaining the same, current changes much. We'll measure the current. About 628.68 amps. 600 to 8.68 microamps. Voltage remaining the same. All of these we can click and drag. Something, let me check what went wrong here. This is exactly the same two numbers. Oh, that's right. 1000, 1500, 2000, yeah. 2500, 3000, 3500, and we can go only up to 4000. I think that should be enough. We just need at least 5 data points to do the graph. Yeah, good. Yeah, it looks good. The error remaining exactly the same because this is a simulated result, right? If you're doing this in person, actually error number going to change. The reason we have to measure the current by using the oscilloscope window. Each time when you try to measure it, you're gonna get actually the human error there, okay, reading error. But that reading error is very minimum in this case. So that's why this number might be remaining the same. That's okay. Okay, then we'll continue 1500. Current every time you have to auto scale and then measure that. Okay. Okay, that's going to be 942.64 micro. 942.64 times 10 to the power minus 6. Voltage remaining the same, doesn't change at all. Okay. We'll do then 2000 frequency. Current has to auto scale. and then you may have to move the cursor for the current. And if you want to see only one wave there, maybe you can decrease the timer, then you can see the expanded curve. That is much easier because I need to put this cursor as close as possible to the max point. Okay. All right, this should be 1.2591 milli, point 0.0012591 milli, voltage remaining the same, and we can click and drag these, it will do the calculation. Let's do 2500. Any question? Current milli 0.0015717. Voltage remaining the same. All of these I can click and drag. Then we'll do 3000. Current is 0.0018776. Actually, all of these I can click and drag. Okay, looks good. Error little bit increases to about 1%, is still very low. Then we'll do 3500. Current point 0021941. Voltage same. All of these we can click and drag. Looks good. We'll do one last data point, which is 4000 Hertz. Okay, current for that case, 0.0024952. Okay, guys, any question? Looks good. So if you look at the numbers, the reactance is 1 over 2 pi f times the c, right? Since I'm increasing the frequency, it is inverse proportionality. So the reactance effect should be decreasing, right? So that's what we see. And it started like 10 to the 4 positive, and then it goes to 10 to the 3, now 10 to the 2, right? The magnitude of that is actually decreasing. So that's inverse proportionality. That's a good indicator. So we can make the 2 grams actually, because we would like to see how the reactants behave across the capacitor as a function of frequency. We'll do scatter plot without any data, and then we'll add the data, select, add, and the X values in this case gonna be frequency for case 1, and the Y values are gonna put measured values, okay, because calculated value gonna be like more accurate, so we'll put the measured values, okay. Measured values, click OK, click OK. That should be inverse proportionality, looks good. Started at very high and then decreasing rapidly, right? So you can put the axis title, trend line, but the trend line has to be changed into maybe like power law to see whether it actually can be connected nicely, yeah. If I use the power law, it should be connected nicely. If you look at the power law equation, for example, that equation will give us what power it actually matching up. We know that should be x to the power -1 power, right? If you look that equation, x to the power x to the power -0.999. So that exactly the number we're expecting, it should be x to the power -1. So the everything looks good. Then we'll put the chart title here. This is impedance versus frequency of capacitor. And x-axis should be frequency in unit hertz. And y-axis is we can say reactance. Actually, that's a term we use generally for the, if I have one item, we generally call it reactance. If I consider both items together or more items together, we call impedance, right? Because of that, I would suggest we'll call it right here reactance. At this point, we are interested only the reactance effect of the capacitor, not the combined effect of RL or the RC circuit, okay? Even though we have the RC circuit, I'm actually measuring the voltage across only capacitor and then calculated only the reactance effect of the capacitor. Okay. Reactance and the unit should be ohms. You can put the unit by using the symbols, okay? All right, guys, any question? Then we'll make it smaller and then bring it here. Make sure if you have a graph, the everything should be fairly visible. Like in this graph, you can see there are certain things. It looks very small, but you have to make sure everything is fairly easy to see. Okay. So now my x-axis numbers are a little bit difficult to see. That also we can readjust. We can go into the x-axis, and the major one we do in each 1,000, the minor one we do in each 200. We can change that into each 500 or each maybe 1,000 level. So let's take a look. Let's do each like, yeah, if I put it into each 2,000 level, then you can see it clearly. Okay, so those things you have to readjust always. Otherwise, when you make a graph and then readjust the size of the graph into your report, then if I can't read those numbers, if someone else reading the report can't read those numbers, then not much meaningful. Okay, make sure everything is much visible. If not, then only option is make sure the graph is larger. Okay, so you can make the graph itself fairly larger scale, then anybody who reading it can read it clearly. Okay. All right, then this looks, I think, good. Then we'll make this graph linear by putting the x-axis into 1 over the frequency. Okay. Insert scatter plot again, select data, and now in this case, x values are going to pick 1 over frequency, not the frequency itself. And the y values are going to still use a measured reactance. Okay. Now that's very linear, right? So there's a lot of data in the very low range, only one data point with it at higher range because that is a 100 frequency point. Okay. That should be very linear. We can put the axis title, trend line. In this case, trend line linear is fine, but make sure all of these three are clicked on. And also I would like to read that number, which is number in front of the X. Since it is showing only one significant figure, maybe it's better to change that into a little bit higher number of significant figures, at least 2 or more, okay? And make sure that is in somewhere, clearly I can see that number, okay? Now with too many sig figs, because it's a large number, so maybe it's better to change this into scientific notation. So all of those you have to readjust carefully, okay? All right, so the axis title is going to be again reactance versus, now this is 1 over frequency. You can say inverse frequency of the capacitor. And it's going to be the inverse frequency 1 over F. Unit C is also 1 over Hertz. it's going to be still reactance units omega. All right, any question? All right, again, my x-axis seems to be numbers going top of each other because it's too many. So I'm going to change that into a little bit, maybe, yeah, that should be good now. So make sure numbers are clearly able to see, okay? Otherwise, it has no any meaning. All right, guys. So these figures you have to rename, right? Since we're going to use 3 of these kind of pictures because we're doing 3 setups, so I need 3 of them. I'm going to name those figure 1, 2, 3. Then we can start this one from 4. Figure 4, this is going to be the graph of reactance versus frequency of a capacitor. And it's going to be about the same here. But this is a different figure. I'm going to name it figure number 5. Reactance versus 1 ohm frequency of the capacitor. Okay. Then we'll take a look how to investigate a little bit in detail the graph with the measured values. Okay. Okay, any question? All right, then we'll continue on to table number 2. In that case, we will try to measure the capacitance by using the graph, okay? So that's a very simple calculation because if I use this graph, then we know this is going to be y equal mx type graph, that is a slope, and then we using the reactance as a function of 1 over frequency, right? This part right here going to be 1 over 2 pi times the c. Then we can say slope of the graph is equal 1 over 2 pi c. From there, I can find the capacitance 1 divided by 2 pi times the slope of the graph, right? So the very simple calculation. Let's do that on table number 2 so that can revalidate all the information we discussed earlier, okay? So capacitor known in unit farad, what's the value? We are using 0.01 microfarad, which means this is going to be 0.1 times 10 to the power minus 6 farad, right? All right, that's a known value, okay? And then from the graph, we'll calculate that. We know from the graph that should be equal 1 divided by 2 times pi open and close bracket for pi multiplied by slope of the graph, which is 1.6 times 10 to the positive 6. 1.6 times 10 to the power positive 6, close brackets, hit enter. So I'm getting about like 0.9 times 10 to the 8, which means if I do that for 10 to the negative 7, 9 times 10 to the negative 7, which means very close to 0.1 times 10 to the negative 6. We'll compare that first, and then we'll take a look. If that is a very large number, we'll take a look whether there's any wrong in any place, okay? We'll compare these two. ABA's expected value is 0.1 times 10 to the power negative 6 minus calculated values from the graph, which is on B number 42. Cross brackets divide by, we comparing this with to the exact value, it is PE, okay? Divide by parentheses 0.1 times 10 to the power minus 6, and then everything multiplied by 100. So it's about like 0.5 percentage error. It looks good. Any question? And make sure percentage errors or percentage differences do not show more than two significant figures, has no any physical meaning, okay? And let's do this calculation function into here. That's gonna be the C from graph. And then percentage error function also we can place here. All right, guys, any question? Okay, then we'll continue. We'll go into the inductor and then we'll measure the inductor again the same way. There's no any new things to do. So we're going to replace the capacitor with the inductor and then we'll do exactly the same thing. And then what we would like to investigate there, whether the inductance whether inductor create the inductive reactance, whether that reactance is actually a function of frequency or not. We know that must be. With our theory part we discussed on chapter 15, we should be able to see that physically. Okay, that's what our plan. So let's do that part here. All I have to do is pop the simulator and then get rid of the capacitor and then put an inductor for that. That's all. We'll replace the capacitor with the inductor. Inductor value we can use maybe about 15 millihenry. 15 millihenry, 15 M. I think we'll do the milli, I think, yeah. Then we'll connect these points. All right, so then again we can simulate and look at the graph. Make sure voltage and current is actually put it into the auto scale, and then we'll investigate first how this react with the change in frequency. We'll go to the zero, very small, and then we'll increase slowly, okay? So as we change in the frequency, you can see now the effect I should be able to see on the voltage or the current, okay? So the voltage seems to be remaining constant, but the current is actually hugely affected again. So which means obviously that confirm that it is depending on the frequency, but if you look at the current curve, what it does with the lower frequency, the much larger, with the higher frequency, much lower, right? So which mean this is actually affected directly, okay? Because we know reactance is measured from the voltage over the current, and the same reactance I can calculate 2 pi f times L with the higher frequency. So this should be actually getting larger and larger. So that is what exactly we actually observing, okay? So that's the idea. Let's take a look. Any question? All right, so let's measure again the same way. I think I can maybe change the cursor number 2 into the current and then place somewhere here. We'll start somewhere maybe low value, how about 500? And then we'll go the same range like we done earlier. Okay. Now we'll do the same way. We'll go around the same range of values which we did earlier. Okay, frequency values, maybe like 500 to 4,000 range, or 100 to 4,000 range. Either is fine. We can start actually at 100, exactly 100. Then we'll go exactly same numbers. Okay. So voltage around here, and then the current around here. All right, then we'll record those on the table number 3, and also I would like to have a picture of this simulator, right? It's a different one now, different circuit. So let's take a picture, screenshot. Usually those pictures must go to procedure section, right? But since we're not doing any lab report with this one, you can leave it on your Excel page. That's why these pictures, I'm going to name it figure 1, 2, 3, okay? Because those are usually must be put it into the procedure section, okay? All right, this will be then technically figure 2. This is going to be RL simulator. All right, then we'll start measuring. Now, what we like to measure is the frequency we are changing, unit hertz. We would like to measure current, unit amps. We would like to measure voltage across inductor, unit volts, and in the impedance, in this case reactance, we would like to measure in unit ohms. Okay. And also we would like to calculate the reactance because we know the expected equation. By knowing the expected equation, we can easily calculate this. And then we'll take a look what we're getting with the calculated values and the measured values. And those two we can compare and then take the percentage difference. Okay, exactly same thing we done earlier. All right, so we'll go the frequency about the same range, not necessary, but that will give us a really good comparison to the previous, right? Exactly same range, starting from 100, and the current I'm measuring through the circuit, which is about like 21.750 milli, point zeros, point only one zeros because in milli 21.750. And the voltage we measuring about milli again, 0.20507, 20507. Okay, be careful with the units and everything. And Excel calculated, which is by using the function, right? We know function is 2 times pi open and close bracket times frequency times the inductance value of 15 milli, 0.015, right? That's a calculated value. If it is larger, make sure we would like to change that into scientific notation. All of these also we can put it into scientific notation since it is smaller values. This too also will put it into scientific notation. All right. Reactance measured, which is equal voltage divided by the current. About the same. Okay, this one is actually even much closer. 4285, 4248. Okay, then we'll compare these two. Equal ABS, open brackets, different between these two. Divide by the average between those two, E48 plus F48, divide by 2, multiply by 100. So make sure percentage differences should be just in numbers, at least two significant figures visible, okay? All right, then we'll record all of these function in here. It's gonna be x of L calculated. It's gonna be x of L measured. And it's gonna be the percentage difference. Again, the same thing, you can just increase the frequency and then see how it behaves. So that's a plan. So then we can look at again by using the graphical view, because then it's much easier to understand what's really happening to the reactance as a function of frequency. Okay. All right, guys, any question? Okay, then we'll continue. We'll change the frequency into 500. And now you know what to do exactly. If it is too many waves, crushing together, then it's not really much meaningful. I need to see that clearly and then make into auto scale. We'll measure the voltage and the current. Now you can see actually both are changing, right? So that's something we did not see with the capacitor. So this is now very different scenario, okay? So you have to record carefully. So now the current value, which is about milli 15335, 0.015335, and it decreases, and the voltage, which is milli 72352.72352, right? And these, I think we can just click and drag. So it looks good. Be carefully investigate. This is the one you need to check first. Okay, if the percentage difference become much larger, even like 5%, that definitely something wrong in our calculation. Here we should get very low percentage error values. Okay, usually less than 2%, definitely. All right, so that looks good. Current passing through actually decreases and the voltage accordingly increases a little bit, okay? And the reactance effect, if you take a look, earlier it's about 9.4, now it's about like 47. So it is now increasing, okay? All right, so let's do 1000. Voltage seems to be match up clearly there, but I need to move this one. But the numbers you have to read carefully. Okay, the current is about milli for 9.5411, 0.00095411, and the voltage milli 904, which means 0.90440. All of these we can click and drag. Looks good. We'll do 1500. Any question? Okay, voltage cursor I had to change a little bit. Okay, and the current cursor also a little bit we need to move. All right. Okay, looks good. Current is about milli 6.68, 0.00668845. And the voltage milli 950.95029. And we'll click and drag this to, looks good. We'll do 2000. So what we really interested is this behavior, right? You can see we know the frequency is now directly proportional to the reactance. So the reactance should actually increasing, okay? So that's what exactly we see. It started at 9 ohms, went to 47 ohms, 94 ohms, now about like 141 ohms. These numbers, we don't need actually, those are not really large values. If you put it into the normal numbers, then you can see that those values, okay? Let's see if the last value right here around like some hundreds level, we can put it into the normal numbers. But if it is thousands, then definitely we should put it into the scientific notation, okay? Any numbers. Okay, we'll do 2500. Any question? All right, the current is 0.0041396 and the voltage is 0.98470. And all of these I can click and drag. Oh, I did 2500. I should do 2000, right? That's why. Let me recalculate that. Okay, let us recalculate this. Okay, 2000. Current is 0.005151 and the voltage is 97275. So let's check it out. Looks good. Okay, we'll do 2500. You have to move for each case both cursors in this setup, okay? Because the both numbers are slightly changing, so we have to measure carefully. Okay, new current point 004 0041185 and the voltage 98231. Okay, looks good. Let's do 3000. All right, the current is about 0.0034990. The voltage is 98231. Did not change at all, but our values definitely should change. Okay, looks good. Let's do 3500. Voltage remaining seems to be at higher frequency values. Voltage not affecting much, but the current is affecting. Okay, so that's something. Those are the observations. If you do in the lab report, those are the ones you have to discuss in detail. What you really observe by doing exactly the same frequency range relative to the capacitor. What changes happen? What's the observation? Things like that. Okay. But since we're not doing any lab report, that should be fine. But those are the things you have to pay attention to. 3500, the current is about 0.0029943. The voltage is about 99187. Very slightly changes, not much. Okay, we'll do one more data point, maybe 4000 frequency range. Voltage doesn't change much at all, but the current changes 0.00260042. Voltage about the same 99187. And let's take it out. The reactances looks good. Okay, so make sure the PD should not be anything larger than 1 or 1.5 because that's actually our reading error where we put in the cursors. If we retry that little bit, we can reduce definitely the percentage errors down to 0.5 or lower generally, okay? Okay, guys, any question? Okay, then we'll take a look at the graph then. We know in this case we are interested x of L which is 2 pi f times the L. So which means we know x f of L directly should be a function of frequency, right? That's what we would like to see. Then we will make a graph frequency versus x of L. We should see a linear graph, then we'll take the slope of the graph, that should be just simply 2 pi L, then we'll calculate the L from there. Okay, then that calculated value will compare to the known or the used value in this circuit. Then if those two are same, that can reconfirm everything we done on this second circuit, okay? All right, guys, any question? Scatter plot, x value should be now frequency, y values now the measured reactance because we would like to use the experimental values. That's why click OK again. Nice linear graph. Axis title, trend line, format trend line. All these three icons should be clicked because we would like to see the equation. And the number in front of x, r is square 1 means it's a perfect data fitting with the given function. Axis title, just chart title, we can say the reactance versus frequency of inductor. And x-axis is going to be just simply the frequency, unit hertz. Y-axis should be reactance, unit omega. All right, any question? And this should be our figure number 6. Figure 6, we can say reactance versus frequency of an inductor. Okay, then we'll take a look. I think all the numbers looks fine. I can read all the x values, y values, and then so on. Those are the ones we had to little bit readjust on earlier two graphs because the graph are smaller in size. X values are going on top of each other. Then you have to always recheck. Okay, after you readjust the size of the graph, those things. Okay, we'll do the known value. We know 15 milli, right? 0.015 Henry. So we'll calculate that from the graph. We know from the graph, inductance should be slope divided by 2 pi. So this is going to be equal sign slope of the graph 0.0947 divided by parentheses 2 times pi open and close brackets. Hit enter. So you can keep 1 or 2 decimal places because we expecting 0.015, we getting 0.015072. So it's a very close to numbers. ABS expected value 0.015 minus from the graph value divide by 0.015 multiplied by 100. Percentage error, make sure only 2 significant figures visible, not anything more than that, okay? All right, guys, any question? X of L from the graph, and it should be the PE in this case, okay? Okay, guys, any question? All right, then we could do more actually. If we want to, we can now go back and recheck maybe two items together, right? XL, we know, creating RL creating itself impedance, right? RC creating itself an impedance, right? We can actually take a look those things too. How the RL combined impedance look like as a function of frequency, how the RC combined impedance look like as a function of frequency. But instead of that, it may be useful to take a look in the all three of them together, okay? Now we know exactly the concept we built on chapter 15 by using phasor diagram is correct. There's no problem about it. Exactly the observation confirmed that. We'll use that idea to further investigate all the items together into a one serial circuit, okay? That's the next part. Any question? All right, that's the last part of this experiment. It's a fairly very easy and simple experiment, nothing much to do at all. So let's continue now. What I have to do, I have to stop this simulator and then build a new circuit, right? So let's go into the schematic and then maybe we can get rid of this and then get rid of that. And then move this one away. I need the RLC circuit, right? We'll put a capacitor somewhere here and then change the capacitor value into 0.1 micro, and then we'll connect this side. Okay, looks good. We'll put the voltage sensor right here because we would like to measure total voltage across all three as a function of current. Okay, that's what we're measuring. Simulate it. We'll put it into the splitter and then we can see the both, okay, graph and this. Now, what we're really interested to see is how the voltage and current behave. Right now, voltage is about close to 1 amps, 1 volt. That's the applied voltage. And the current is somewhere, let's put these two cursors first to see. We'll change the cursor number 2 into current and then we'll place it here. Current is right now about like 20 milliamps, okay? Now the frequency is 4000. So let's bring it to the lower value, like maybe 500 or 200, okay? And then we'll increase from there slowly to see whether that observation we discussed earlier in last chapter, when I have RLC circuit, whether that's the same observation I can get here or not, okay? Voltage, it's about is still the same, okay? Now I changed the frequency already 4200 level, voltage doesn't change at all. But the current seems to be changing much. Right now, current is about like some micro 100 or so microamps. If I bring this to maybe like 500 hertz, then you can see current changes much. So let's auto scale the current and then measure the value. Now again, like it is 300 or so micro. Let's bring this to maybe like 1000, 1 kilo range. Let's change the current and then take a look at the value. So now it is about like 665 micro, it decreasing, right? So which means my resonance frequency is not there. Let's try like maybe 2500. Because we know current should be maximized and then decrease again, right? That's the observation. If I don't see that in a certain frequency range, then it's not meaningful doing that experiment at all, okay? Current, now it is in milli, so it's still increasing. So let's do milli 2.5, okay? Let's do 4000 frequency range. Let's auto scale the current. Let's check it out, the current max. Now it is in 20 milli, so it is still increasing, right? Let's do this maybe, how about 6000 frequency range. Now if I take a look at the current max, now it's about 3 milli, okay? In 4000 frequency range, 20 milliamps, 6000 frequency range, 3 milliamps of current, voltage remaining the same, which means somewhere in between I have the maximum current where the frequency is actually going into the resonance point where the current becomes maximum through the circuit, right? So that's the idea, which means that search is very difficult to do in general because it's a trial and error if I don't know about the resonance at all. Theoretically, I don't know the expected value at all, then I have to do that scanning from one frequency to another. It's a very, very difficult process to do. Okay, that's why depending on the numbers you use for the inductor and capacitor, that resonance frequency value change. We know that is 1 over 2 pi LC square root. So I have to first know that number and then get an idea which frequency range I should search for to observe that particular behavior. Okay, that's important. Okay, then this good, which means if I go like maybe 500 to 10,000 range, then I should be able to see this behavior, right? So if you go into the lab manual, it will suggest you a range of frequency starting from 500 goes to like maybe 6,000, but around the exact that resonance frequency point, I need more data. Okay, so that's why it's asking you to get more data around maybe 3800, 3900 to maybe 4100 level. You see, it's suggesting you to take more data like each 50 hertz or so. Okay, otherwise, we can go 500 in the beginning. When we close to the max point, we can go maybe 100 or maybe 50 hertz increment because I should be able to see that curvature nicely, okay? That's the idea. Any question? All right, then let's continue. So we'll use around the same range. Maybe we can go from 500, each 500 beginning. After about 3500, we can go a little bit smaller values, 37, 38, 39. 39, 50. These numbers we might be needed to change slightly. We'll first follow these numbers and then see whether we can see that nice curvature on the top. If not, we may need more data there, okay? 4100. 4150, 4200. You can take any number of data after that or in between, doesn't matter, but that curvature is the one we're looking for, okay? All right, then we'll go here and then we'll take a look starting from 500, okay? All right, so the current is as usual measured with unit amps, voltage, unit volt. In this case, we call impedance because now we know we have more than one component. So we are actually talking about equivalent resistance effect. So that's why we call impedance now, okay? If I have one item only, then I can call it reactance. Unit ohms. And the same unit. Okay, and then we'll compare those two because we know the expected equation. So R is square parentheses XL minus XC to the power 2 is square root of everything. So we can calculate the number and then we can measure the impedance by using the equivalent effect. And then we can compare those two. After that, we can actually take a look at maximum point also. Okay, that's a plan. We can investigate both of them. So we have R, L, and then C together. But what we're measuring is the voltage from here and the current passing through this whole circuit, which means if I assume all of these will create some sort of equivalent resistance, that's impedance here. Then we know the voltage, we know the current passing through. If I apply the Ohm's law for this guy, Z is equal total voltage over total current. That will be the measured value, okay? Calculated value, we know from our equation which we develop, R is square plus X of L minus X of C to the power 2 is square root. Then we know this guy is depending on the frequency, right? So then we can compare these two together. We expecting those to be about the same. Okay. All right, guys. Any question? Okay. Then we'll start measuring. We'll take a picture of this one too. This is a different circuit now, right? We'll collect that into here. Give me 1 minute. I just need to reopen the Excel page. That become very slow, almost look like it's stuck. We'll reopen that. Should be usually should work fine after that. Okay. All right, let's put a picture somewhere here. Maybe it's better to make sure it's better to have a nice graph too when you're putting the picture. I need to auto scale this too and then observe the curve waves nicely and then put the cursors in the right location. Then we'll take the picture. Okay, that looks good, I think. All right, so we would like to have our circuit and the graphs. And this should be actually figure 3. Remember, we're naming those according to general way of where these are usually putting in. So this should be then figure number 3. This is RLC circuit, okay? Okay, then we'll continue to our table number 5. Any question? Okay, frequency is 500 and the current we measuring is about 318.93 micro equal 318.93 times 10 to the power minus 6. Make sure you put this into scientific notation. It's a small number. And also make sure all the significant figures measuring are visible, which mean the 5 sig figs, okay? And the voltage we're measuring should be exactly close to 1 volt. We'll take a look. If you adjust this a little bit, you will get exactly very close to 1 volt, okay? You have to bring the cursor, green one, all the way to the very top, 1.0062. That 0062 is actually our measurable error, human error, okay? Then we'll calculate C and then by using the equation and the measured value. Okay, from measured value, this is going to be very simple. Equal voltage over the current, right? So that's a simple calculation. And then let's do the calculation by using the equation. Equal sign SQRT, that is the square root, open brackets, resistor to the power 2. Resistor in this case, we are using 45 to the power 2. Plus open brackets, another open brackets, and 25F times L, that is the reactance of the inductor, 2 times I open close bracket times the frequency which is the cell number B88 multiplied by the inductor we are using 0.015, right? Milli 15 close brackets minus another open brackets 1 divided by 1 over open brackets 2 times pi open close bracket times frequency times the capacitance, which is zero point 0.1 micro, which means 0.1 times 10 to the power minus 6 close bracket for that denominator, then close bracket for outer part, then close another bracket, then you have to put power 2, and then close another bracket for square root, okay? And then hit enter. And also, since these are large numbers, we can put scientific notation for this one also. And we can use maybe 5 or so significant figures. Then if you look at the two numbers are extremely close by, okay? So let's record these. That's the function we created for the impedance C for RLC circuit. And this is the function we use for direct measurement, assuming the equivalent resistance that we can say Z measured. The previous one is actually Z calculated. And then we'll do the percentage error. We'll compare those two equal ABS, open brackets, one minus the other, doesn't matter which comes first, divide by the average between those two, E88 plus F88 divided by 2 multiplied by 100. And the percentage error, make sure in normal numbers with only 2 visible significant figures, okay? All right, guys, any question? All right, then all you have to do now, make sure this first row you do very carefully and then looks everything before you collecting the rest of the data, okay? Because if that is incorrect, then everything has no meaning. But if this row shows you all the calculation and everything looks nice, then I can continue the rest, click and drag for the calculation. That is much easier to do, okay? All right, then we'll take a look by slowly increasing the frequency. We'll go 500 at a time first. Next 1000 hertz level. The current we can put it into the auto scale, voltage remaining the same. Current now, which is about 665 micro, equal 665.39 times 10 to the power minus 6 micro. Voltage remaining the same. These three you can click and drag, okay? So that percentage different number is so important because carefully take a look that if that shows something wrong, then we know something wrong in our calculation, okay? And then that's it. It's very simple. We'll increase this 500 hertz at a time at this point. Voltage remaining the same. The current is changes. Now it is in milli range. It increasing, right? So it is on 1.08 milli. 0.001087 milli. Voltage is exactly the same. This we can click and drag. Looks good. And impedance, if you look carefully, impedance is actually decreasing, right? That's what we're expecting because where the current maximum happens at that exact moment, we know power through the circuit becomes maximum, right? So when power maximum happening, the impedance is actually becomes minimum because total impedance exactly at resonance point is actually just the resistance. Even though capacitor and inductor there, those two look like not creating any resistance at all. That's the very specific feature of this experiment, this part of the circuit, right? So which means now impedance slowly decreasing, right? So that's the idea. Okay, let's continue to 2000 hertz. Put the current into the auto scale, then measure the maximum current, which is now 0.00164005. Voltage remaining same. And these we can click and drag. Looks good. Decreasing impedance. Let's do 2500. Any question? 0.002468 is the current, voltage remaining the same, and these three we can click and drag. Let's do 3000 hertz. And the current is 0.003986. Voltage remaining the same. Looks good. Let's do 3500. Voltage remaining the same. Current is now 0.00766635, right? You can see current increasing by large numbers now. Looks good. Let's do 3700. Voltage remaining the same. Current is now 10 micro, so it's much larger now, 0.010927. Voltage remaining the same. We check it out, the impedance now getting much lower. Okay, now it is just 93 earlier, about like 132 in the beginning. With the lower frequency it's about like 3000 ohms. Okay, all right, let's do 3800. current is about 0.013509. Voltage remaining same. Looks good. Let's do 3900. Current is now about 16 milli, 0.016941. Voltage remaining the same. This we can click and drag as usual. Any error is actually reading error, okay? Because I have to place exactly, we are close to that peak point. So that is small difference create that error, okay? We'll do 3950. Voltage remaining same. The current is about 18.7.0187. Okay, let's do 4000. Current is still increasing, 20 milli, 0.02062. Still increasing, but now increasing slowly because we increasing frequency also very slowly, right? That's why. Let's do 4050. Still, I think increasing very slowly. Yeah, 21. 021750. That's good. Let's try 4100. It's still increasing very, very slightly. 22 now. Let's try 4150. At some point, we should see it is starting to decreasing. Okay, see that cursor, blue cursor, C2, is on the previous location. If I go back to the 4100, earlier number we did 4100. So that's where the current is. Now, if I go to 4150, now that's where the current is. Current is starting now going backwards. So now we cross actually that maximum point, right? So that's the important point, important part on this, because we need more data on that range, maximum range, okay? All right, now current is starting to going backward. Again, 0.021654. Let's go back to the previous number. Now the impedance decreases and then now it's starting to increasing back, okay? We'll do 4200. Current decreases back again to about 20.22. Okay, and then the accordingly impedance should now starting to increase slowly, okay? Let's check 4500. 4500, 11 milli now. So the current is now decreasing by large, okay? So that reconfirming the range of data we actually collected earlier, I think should be good enough to see that curvature point, okay? So that's important. And then that's it. Then you continue likewise. So let me take a look. 4200 again. Error is a little bit higher. to see whether I did any mistake on my number 20.315. So let's check it out, this one. Okay, it's about the same, I think. That has a little bit of larger error, probably. Only reason is actually reading error, nothing else can be anything wrong in this case. So you can try to recheck a couple of times to get the as accurate as possible. I think 20.315 is the one I can read. That's okay. So let's do 4500. 11.520. Looks good, but the error is a little bit higher actually there. 2 again. And let's do 4800. 7 milli, 0.00744092. Voltage must remaining same. Good. 5000. 0.006163. The error is little bit higher on that range. Now it's getting fine, I think. Decreases, usually it's remaining 2% or less. Because the error is only coming from our reading error, okay. 5500, current decreases more and more. Now it's about only 4 milli, 0.00415887. Voltage remaining the same. Looks good. Error is also lower now. And we'll take a look one more data point, 6000. You can take few more if you like, doesn't matter. I think we have good enough data to make the graph. 0.0031731071. And let's take a look. Okay, so that should be good enough data. A couple of points, I think I have the errors a little bit higher, 5% on one and 6% on another. Otherwise, it looks fine. So now the idea what we're really interested is not just this impedance calculation. What we're really interested is to see that resonance point, right? So let's take a look at the resonance point. So to do that, what we need, we can make two graphs. We can take a look how the current is actually behave as a function of frequency. Let's do that first because that's the graph we needed to understand where the resonance point is. Select data and X values will put the frequency range, which mean the column B, all the data points. And the Y values, select the current in this case, okay? And click OK again. Now this should be showing us some maximum point. This is not regular parabola, okay? You can't fit this data to the regular parabola. This is like a singularity, right? It goes very sharp and then going backward again. So I can't fit the data and then get that answer. That you can't do. So what we have to do, we have to read the maximum point, exactly identify the maximum point coordinates on X and then read that number on my x-axis. Okay, that's the only way to read that number. And if you make another graph, we'll make another graph, insert, scatter plot. We'll make in this case frequency versus impedance, okay? Frequency range, column B, and the impedance measured value, okay? Not the calculated, measured value. And then click OK, click OK again. Now we know impedance on the other hand should show a minimum, exactly that point, right? You can see right here, it actually becomes it little bit broader, not like the current. Current shows a nice sharp peak, but the impedance also show the same minimum point at the same frequency, but it's not sharper like the current. Okay, that's why we usually going to use the current versus frequency get that resonance effect. Okay, because what really happening in the circuit is actually the power. Power becomes maximum at that point. That happens because of the current becomes maximum. That's the idea. So you can don't fit this data. Okay, there's no meaning fitting this data. And as usual, you can put the axis title, but don't add the trend line. That's not meaningful. So axis title graph, first graph, we can say current versus frequency of RLC circuit. In this case, x-axis is frequency. Unit hertz. And the y-axis is the current, unit amps. Okay. And the other graph, we actually drawing impedance versus the frequency. And in this case, axis titles, x-axis is still frequency, unit hertz, and the y-axis in this case is impedance, okay? Total impedance of the circuit. Impedance, unit hertz. Okay, any question? All right, so those two graphs don't fit the data. That has no meaning. Do not put the trend line, okay? We cannot put the trend line for this kind of graph. These are not regular parabolas. You're not going to be able to see any nice fitting at all. You have to name the graph, okay? The last one right here, figure 6. So we can name this one is figure 7 then, right? It's going to be current versus frequency of RLC circuit. And the other one should be now, this is 7. This next one should be 8. This one should be figure number 8. That should be then impedance versus frequency. Okay, so looks good. Now, only thing I have to do is to figure out the resonance frequency by using this current versus frequency graph. Okay, now what I really wanted to do is identify. You may have to manually maybe enlarge the graph. I have to exactly see this maximum point right here on the x-axis, right? Now, x-axis, you can see numbers are a little bit further away, which means I have to put more numbers, more closer numbers there. You can do that by double-clicking on the x-axis scale, and then maybe we can put minus majors. Now we're putting like each 1,000. Maybe we can put each 500. Yeah, much better data. And we can put maybe like each 100. Yeah, now it's better. So we should be able to understand how that behave. Okay, guys, question. which may be 200. Okay, so we'll use each 100 and then we'll select the scale. We interested only that maximum range, right? We can select maybe like 3700 to maybe 4500. Okay. Now we'll expand again the scale. Now we can put maybe each 50. Now that's the data analysis part. Now, if you do this kind of work with the like little bit advanced data analysis tools like MATLAB or Python or any other advanced data analysis tool, it is much easier to get this maximum point. Okay. Now with the Excel, I can't do those things. There's no any command I can give. I have to really work around. So that's why I zoom in, then the range where I interested, now I can easily see where's the maximum point, somewhere here, right? So if I go down and the x-axis, if I read the value, that should be close to 4100. It may not be exactly, that's okay. That's the value I can read with my data. So I'm going to read that number. If I want more accuracy, what I need is more data here. So you have to collect the more data point here, like maybe each 10 frequency range by increasing each 10. And then I have to look at it whether I can pinpoint that maximum current location. Okay. I think this should be good enough. That will be our reading error anyway. So I'm going to read the resonance frequency as 4100. Okay. So that's the plan. So the measured frequency from the graph, unit hertz, which is about 4100. So then we don't need actually the rescaling we done. We can go back to the auto scaling. Okay. We can reset all of these. Then this will auto scale everything. Okay. And then you can make the size go back to the normal size of the graph, which we used earlier. Keep this graph close by here. Now everything looks good. Only thing I have to do is to calculate the resonance frequency from our formula. You know the formula for the resonance frequency for this particular circuit, 1 over 2 pi LC square root of that, right? We'll check it out that. Any question? Two times pi, then SQRT, open brackets, L is 0.015 times, C is actually 1 times 10 to the 7, right? So I can just put 1 times 10 to the negative 7, close bracket for SQRT, close bracket for the denominator, hit enter. So the number we're getting from the calculated value, 4109.363. So that's very close number, okay? So we could get more closer if I go more smaller data range, the increment range, in that range of the maximum on the curve. Then if I get more and more data, then I can get more better answer. So that's the experiment process. You have to take a look at the graph. If data is not enough, you go back and then collect more data and then recheck the graph, okay? Then that's it. Then you compare this directly. That's it. So this is going to be, we can say 0 calculated. Then we'll compare these two equal ABS open brackets. Calculated value is the expected or the known value, right? Minus the value from the graph, divide by the calculated value C132 multiplied by 100. So make sure percentage error visible only two significant figures and function we can collect into here. Okay, guys, any question? All right, so I think it looks good. everything, we completed every single calculation. Okay, make sure there's 3 pictures from the simulators, and then there's 8 different graphs we make. So all the graph must be visible. 5 different graph we make, so altogether 8 figures, which mean, and then there were 6 tables in this Excel sheet. Everything must be completed before midnight tomorrow, and then submit them. And couple of other things in this week. Now, today evening, we'll take a quick break, then we'll continue mid-exam 5, and then we'll continue tomorrow, chapter number 16. That's the last chapter. And then tomorrow, later session and the Wednesday session going to be the review. It's optional. You don't need to log in unless if you have any question, you can log in. I will be online through the class session, regular class session. Okay. And then on Thursday, you're going to do the final exam. Then hopefully by the weekend, your final grade should be ready. Okay. So that's the plan. Okay. And then there's a couple of surveys. I think you can do that on this exams and survey folder. Each survey, it's about like not much. 0.5 point on for your final exam grade, not to the final grade, okay? Final exam grade. You can do them before the midnight Thursday, okay? All right, let's take a quick break and then we'll start the exam afterward. Let's take maybe like 10, 15 minutes max.